Alright, so we're going to talk quickly about just polynomial functions, which will lead us into down the road our calculus concepts of limits and derivatives. But basically we're talking about smooth continuous functions, so these are things that you're used to like parabolas or cubics, but that we have no kind of sharp corners on these things as they go up and down. And we look at, the first thing is that we look at the end behavior of these, so this goes up and this one goes down. They have opposite end behaviors. This one has the same end behavior, they both go up. And that leads us to look at the highest exponent, often what we call the degree of the polynomial, will tell us things about how these work. We have critical or extreme points. These are the high and lows, the hills and the valleys within here. We have an increasing branch, which means as you go from left to right, you're going up, and if you're decreasing as you go from left to right, you're going down. So you imagine increasing, you're going uphill, then downhill, and these are called critical or extreme points. And then these are going to allow us to really determine the end behavior by just looking at the coefficient of the highest degree piece. And we'll look at some examples in a minute. Our notation here is as x goes to infinity, so that would be on this side as we're getting to infinity. What is the function doing? What is f of x doing? And then we'll also have as x is going to negative infinity, what is our function doing? And those two things are going to allow us to sketch these graphs pretty quickly and accurately. So you can see here's a polynomial, degree of n, and then it just counts down to finally some constant value that doesn't have an x attached to it. And if we have an even function, what we're going to figure out is that both of these go up at the end. And this assumes that this a value is larger than 0. If n is even and a is less than 0, like a -3, then it's going to go down as we get down there. If n is odd, one goes up, one goes down. And if it happens that a is positive, this will go up, and then our left side will go down, and it just gets flipped over when we do it the other way around. We just throw a notation on that. As x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, right, f of x goes to positive infinity well. And it's the same idea for the other one. As x goes to positive infinity, f of x goes to negative. As x goes to negative infinity, f of x goes to negative infinity. And these are our even functions, where with this degree here is our even value. So 2, which would be our quadratics, 4, 6, 8, all the way up. And then same idea down here, right? As x goes to negative infinity, we'd have f of x going to negative infinity. As x goes to positive infinity, f of x, the function, goes up to positive infinity. All right, and then our reverse ones for these ones here. And that's in odd degrees. So a cubic, 5th degree, 7th degree are going to have the same piece of view. All right, so then we have something that deals with the roots. We have something called the fundamental theorem algebra, which basically just says that a function has at least one zero in the set of complex numbers. So we have different terms for zeros. We have roots, we have factors, but basically what it says is if we have a 3rd degree polynomial, there's going to be 3 roots if we deal with the complex numbers. Or a 2nd degree, there's always going to be 2. Whereas just with the real numbers, with the non-imaginary components, we may or may not get all those roots to come back. And we'll look at an example down here and see what that's talking about. So those are the roots, also the zeros or the factors or the intercepts. And those are the values that we're looking at. We can see there's 3 there. And we can look at the behavior of this and see that it's going to be some odd degree function because we have opposite end behavior. And so what we want to look at is we have a minimum of 3, but we also notice that we have this other kind of curvature here where we have a high, we have an extreme point and an extreme point. These are going to be our complex roots. And we can see over here that we know if we have one complex number, then we're going to have what's called a conjugate pair. So that means if I have like 3 plus 2i, I'm going to have 3 minus 2i as a root as well. And we'll talk about how that looks in a minute. But again, we'll have that multiple of 2. So I'm going to have 2 of those. I'm going to have odd, which means that I'm going to have a minimum of 3, possibly 5, possibly more. But in this case, we'd have 5. We know that the leading coefficient is positive, because as we go to infinity, this goes up to infinity. And so that's our positive value. I know there's 3 real zeros because I can see them right here. There's 3 real zeros. And then there are going to be 2 complex zeros, which means that my degree is going to be 5. All right, and we could sketch some values of this, and that's what we'll look at when we meet up again.